Okay, so we'll start now. Start discussing the quiz questions. Okay, so let me not the I should not see the preview because preview doesn't show me. I should do the edit. I think Kamod, I mean, this feature is a bit cumbersome also. I mean, anyway, it's fine. I had never done this before, so I'll just share my screen now. Okay. I will share. I think I should share the screen. Okay, I think I have shared the right screen, right? I had too many screens opened. You can see the question. So you can also see all the 3 questions I had put for example, question number 1. Is this fine? Can you all see it now?
Yes.
Okay, excellent. Okay. So first question is basically discrete time population model, and I'm asking what is the interpretation of G prime n star? Okay. So this is a 5-mark question, and I was expecting a single phrase answer. So which is basically G prime n star denotes, what does it denote? It's basically the per capita growth rate of the perturbation from the equilibrium. That's the most precise answer. But most of you have interpreted this question slightly differently. You basically have gone on to say that using this value G prime n star, we can calculate stability. If it is greater than, if this modulus is between -1 and +1, it's stable. If it's outside, it's unstable. Okay, which is also right, by the way. So I haven't. So if your answer had the very clear phrase, because this has nothing to do with. I'm not talking about specifically how do you use it, right? I'm just asking what's the interpretation of this specific term. So if we have written per capita growth rate of the perturbation at equilibrium, I have given you full 5 marks. If you have written the standard stability analysis, I may have given you 4 or 5, depending on how clear that phrasing is. Okay, and exactly same for the third part here. It's basically F prime x star is also per capita growth rate of perturbation from the equilibrium. Okay, but this is just a continuous time model. Okay, and the middle one was much less. It didn't have the slight trick that the other 2 had. This is basically per capita growth rate. So that was first question. Okay, so now why do I ask this question? Because it's really important to understand, as I have emphasized several times, what is per capita growth rate, what is growth rate. That clarity is really, really important, and often that is what you can also measure in experiments. Okay, and that is also what is important for understanding density dependence. Density dependence is something that's measurable quantity, right? Again, that's why I had another question in one of the next sets. Okay, this was question number 1. So any quick comments or questions about this question? So unless you have done a blunder, you would have received 4 or 5 marks in this question. Okay, so I'll move on to the next question now. So next question had 3 versions of very similar equation. So the first equation is nt plus 1 is lambda 0 nt divided by 1 plus a nt. Okay, so this is also called, by the way, Beverton-Hort model, which is one of the another important model in the context of population biology in the discrete time dynamics. So the basic idea of this model is that nt plus 1 divided by nt, the density dependence, right? That is constant lambda 0 divided by 1 plus an. And the idea is that it actually decays with the, in a hyperbolic way as a function of the population size. Okay, so remember in the logistic model, what is nt plus 1 divided by nt? That's a linear decay, right? And that hits 0. On the other hand, this would be a hyperbolic decay, which has a sort of 1 over nt form, but with a constant. That way, at nt is equal to 0, you don't have a problem. Okay, so that's this question. So I thought, okay, let me just modify it to have n square and n cube. So those of you who got this would have had to unfortunately do slightly more algebra, but they're all roughly equivalent. Okay, because you have to do two terms differentiation anyway in all of them. So for this question, if you just blindly do stability analysis, you will get that lambda 0 is between -1 and +1 for stability, okay, of extinction equilibrium. Okay, so I think a large portion of you have gotten this right. At least, you know, have now gone through 23 papers. I think most of you have gotten this right. In fact, all the three of them. And for the next two questions, lambda 0 can be anything, and the extinction equilibrium will be still stable. Okay, but here is a small catch that I think even I overlooked when I was writing the model solution, which is that you have written, let's look at the first question. You said lambda 0 can be between -1 and +1, right? If you apply the criteria. What if it is, let's say, -half? What happens if it's -half? Let's say NT was some value. What happens to the right hand side now if lambda 0 is -half? What is NT plus 1?
Like you get a negative value, which
you get a negative population density, right? So if you had written this very carefully, not just thinking mathematically, you should write that lambda 0 basically should be between 0 and 1. Okay, but I haven't cut marks for that, but just keep that in mind. Especially this becomes very relevant when you try to model real biological systems. You have to make sure, as we discussed while model building process itself, right? Whenever we write down an equation, we think of what are all the possible ranges that the parameter can take, and then we work within that domain. Right? Likewise, here lambda 0 must necessarily 0 or above positive. Okay, so strictly the biologically correct answer is lambda 0 is between 0 and 1. Okay, including 0. But it's fine. I haven't cut marks for saying -1 to 1. Likewise, here I think I don't know. I don't think a single person has said that lambda 0 has to be above 0 for any of the questions. But this is something to keep in mind. Okay, and for this one, a lot of people have written -infinity to +infinity, which again is technically not the most accurate answer. But mathematically it's fine. Mathematically it will indeed converge. Okay, so that's the second question. Any doubts on this?
So I had one doubt. So when I was trying to, like say, at find equilibrium, I felt that 0 wasn't an equilibrium because if you make n t plus 1 n star and everything n star, you get 1 plus cnt is equal to lambda nt cubed or nt square, sorry. And then you get 1 on one side and 0 on the other side. And does that mean that 0 is not an equilibrium?
Did you cancel NT, by the way, before doing that? You must have cancelled. Which question did you had, by the way?
Square of the cube? 3.
3.
Yeah.
See, basically, just look at this, right? Now, if you just replace NTs by n star,
yeah.
You have n star is equal to lambda 0, n star cube divided by 1 plus cn star, right?
Yeah.
So the first step that you have actually done is you have cancelled n star on both sides.
But not full, right? That's n star cube. So you still have n star square left behind, right?
So the idea is that you're taken a common factor of NT, right? Yeah. What does that mean? That's the 0 root that you have actually taken out first. That's the 0, root. Basically, just think of it as an equation of this type: x into 1 minus x equal to 0. Or let's think of something simpler: x equal to x square. Yeah. Is 0 a solution for this equation?
Yeah.
Right, it's something similar, right? N is equal to n cube.
What if it was x equal to 1 plus x squared?
That is not what you have though. You have n is equal to n cube by 1 plus n, right? I'm ignoring the coefficients. Okay, so if I put n is equal to 0 on both sides, the equation is satisfied. Both of them will become 0, right? So 0
I was taking the denominator to the other side, because that n star and n
That
star
is fine. That is fine.
Yeah.
That is fine.
So, and then when you make n star equal to 0, you get 1 plus c n star on one side and lambda n star square on the other side. And then when you make n star 0, you get 1 on one side and 0 on the other.
Maybe I can explain this separately with you later. Is that okay?
Okay, sure.
Sure. Yeah. Thanks. Yeah.
So I also had a question about the same.
Sure.
So can we say that the equilibrium does not depend on lambda's value instead of saying, say, lambda can be any value between infinity and
That's also they're both valid answers. Yes. Yeah.
Okay.
Yeah. You're right. Basically, that condition becomes 0 for all values of lambda anyway, right? So that means it doesn't depend on the value of lambda. As long as you have chosen a lambda that is biologically realistic, it's fine. Okay. That's question number 2. Let's go to 3 now. So 3 had, I think, 4 parts. Okay. They were all, again, trying to sort of, these are all useful pattern to keep in mind when analyzing data. For example, if you know that there is a population that exhibits 4 cycles, how would this plot look like, right? That's a very useful thing to know, right? Okay, and I think my model solution will come up if I just do this. Okay, this is what I wrote. It could be, the basic idea is that a 4 cycle will appear as 4 dots, or maybe a cluster of dots if there's some stochasticity. So what some of you have done is you have actually done simulations and plotted it, which is also fine, which is actually correct answer, but I would not say the best answer. Okay, it is a plausible plot because you have actually done simulations, which means the question had room for what you have done. But ideally, I would have liked to see a graph like this, or maybe 4 clusters. The idea of a 4 cycle is it's switching between 4 points in a periodic way, right? And if so, they will, if you look at data in such a system, the data will cluster around those 4 values. That's the basic idea. Okay. And okay, this is a question which again is one of my favorite questions. I keep asking this because it's very easy to do mistake. What is a density independent growth and what is a density dependent growth? Okay, so density, we always remember this. I have emphasized this. Density independence means that the per capita growth rate is constant. The most common mistake is to think that the growth rate is constant, and indeed some people have done this mistake. So for this question, this is constant. So therefore, d by dx by dt as a function of x will be a linear function. Okay. And this is another question about 2 cycles. 2 cycle likewise should have how many clusters now? 4 cycle had 4 cluster of points. 2 cycles will have 2 cluster of points. Then you do xt plus 1 versus xt. Okay. I mean, I haven't cut marks if you have actually simulated and plotted a few more here. But here I was just expecting a schematic. I wasn't really expecting that you actually do simulations of the logistic model. Is the idea clear?
So the two cycles should be just clarification.
Yeah.
So the 2 cycles should be symmetric around the x equal to y axis, right?
I mean, that's
keep exchanging
you're probably right. You might be right about this, but I'm not entirely sure about this myself. Primarily because it is symmetric around the bifurcation point, which actually is unstable. What I don't know is if it is symmetric around in this graph. You see my point? See, when you see that branching diagram, right?
Okay.
There it is symmetric around the bifurcation by r minus 1 divided by r line. But I don't know if it is symmetric around this, in this. Okay.
Okay.
I don't think it is.
Okay.
But that's if this is a good point though. Broadly, there will be some properties that even 4 and 2 cycles will follow. But I wasn't going into that level of mathematical precision in these questions because we haven't covered them anyway, right? We were only looking at some qualitative patterns here. Okay. So the last question is again about density independent, but asked in a very different way. If you now plot, 1 over y dy, what is it? That should be a horizontal straight line. Okay. The density independence. Okay, so just this is a very important thing to keep in mind, because this is something people do measure in experiments, especially in the laboratory experiments. Who study population dynamics. Okay, excellent. So now I go to fourth question. I think fourth question was fairly straightforward. I don't think anybody had problems at all. Okay. So I think most people have written reasonably well. So the only point that I have written in my answer is that resilience is of at least in the way Halling in 1960s and 70s defined was is defined as the maximum perturbation that an ecosystem state can absorb and still stay there without changes in the overall ecosystem state. However, stability is measured for small perturbations, at least the way we have been defining stability in the class. Of course, there is also a concept of global stability. And when we think of global stability, the resilience and the way ecological resilience is defined and the way stability is defined can become very similar to each other. But I think most of you have written this. We have also highlighted other factors like the stability is applicable only for equilibrium points. It doesn't care about how many other equilibrium points are there, whereas resilience actually accounts for that also. It's all valid points. So I think most of you have done well on this question. Okay, but I think one thing I noticed was that some people were jumbling up a few words. So it's because there are so many words that need precision here. What is a perturbation? And what do you mean by intense? Some people use the word intensity, resistance. You need to be clear about what those things mean, because some people also use those things to mean very different things. Okay, so it's important to avoid words that are unnecessary. That's about question number 4. Okay, so now comes the most difficult question, long question also. So there were 2 versions of this question, which had sort of opposite patterns, but but the principle behind them is very similar. Okay, so I think I'll just change the screen now and share some of the screen. Okay. I think I'll share this. Can you see this?
Yes.
Okay. So let's discuss this question. A troop of monkeys are wandering around, influenced by some deterministic and stochastic factors. The student writes a mathematical model of the form dx by is equal to f of x plus g of x eta t, where x is the centroid of the troop. Fx is the deterministic driver. Gx is the multiplicative noise term capturing the stochastic driver. Eta t is Gaussian uncorrelated noise with 0 mean and unit variance. I know it's quite mouthful, and you have studied this only last week. Okay, so I have been fairly liberal in grading this, unless you got many parts wrong. Okay, for example, I don't think anybody got it's less than 15. I mean, okay, some people may have gotten less than 15 if you did not do anything at all. But if you have made any reasonable attempt, you have got 15 and above. So I haven't stuck to this exact marking schemes here. Okay, so but I have given one number, but unfortunately you may not know the breakdown. See, for example, I was really surprised that, okay, let's go one by one. The first part here I thought was fairly easy, but surprisingly a lot of you did not write it very clearly. I'm a bit puzzled why. Is it because you came here very late? By the time you came here, you're already done with you have already spent a lot of time. What was the starting time for this question for many of you? Give me each of you.
For me, it was like the last 10-15 minutes.
Oh,
typing the equations took a lot of time. I couldn't type equations.
Oh, okay. So the previous 4 questions took a lot of time, is it?
It was not the question per se. It was just typing the equations.
Typing took a lot of time. Okay.
And
Okay.
even the plots also, I had to make them by using.
I
So
see.
I couldn't attempt most
Yeah,
part
yeah,
of
I
it.
agree. These issues are, very, very serious. I mean, I agree, which is why I didn't want to give a huge weightage for this. I will also try to see what we can do to sort of, if we, I understand that there are real constraints. Typing equations is a very cumbersome process, and also making plots is also a cumbersome process. But anyway, don't worry, because this is not like a typical midterm where 1/3 of your, or maybe even more marks comes from this. So this has a very low weightage. We can even reduce the weightage if you like. Okay. So
another issue. Hello.
Yeah. So can you finish going through the question? Maybe then we can ask other questions. Is that fine? Let's focus on the science part of it first. Is that fine? Any questions about statement of the question, by the way, that you can ask? So it looks like a lot of you have had taken 1 hour to finish question number 4 questions, right? Which I was not at all expecting. So I was expecting, okay, this is one sentence, right? I knew second one had some calculation, but as I said, I did not need the steps. I only of the derivation, derivatives, for example. Okay. This was literally a graph, right? So maybe, but you're right. I was absolutely wrong in sort of estimating how much time it will take. I was expecting that the first 4 will take 30 minutes, and you have basically 30 to 45 minutes for the last question. But I know I was clearly wrong about that. Okay. So let's try to understand this question. So any doubts about the question? Is the question clear? So we have, I think one confusion that would easily have happened was that we have been discussing X as population density all throughout, and suddenly X becomes location of an animal group now, right? That's a sort of mental shift we have to do, which I am sure takes time and to get used to that thinking. Okay, but let's see. Given that, is this fine now?
That was really a googly, actually.
It was actually what?
Googly, I said. I mean,
okay. 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 Now let's read A. To model the deterministic part, a student assumes that the troop follows the equation f of x equal to minus alpha x. The system had no stochastic driver. What is the plausible interpretation of the resulting equation and the parameter alpha? So I'm basically asking you to do this now. So somewhat surprisingly, a lot of you have actually not done this well, which was quite surprising to me. So because this is basically telling dx per it is equal to minus alpha x, right? Something the first equation we studied in this course. So maybe because you had already taken so much time and you were a bit nervous about finishing it on time. I think that may have been the reason. So let's look at my model answer. Okay. 0 or origin is a deterministic stable equilibrium point. Is that correct statement? Dx per it is equal to minus alpha x, right? Hence, monkey troops show a deterministic pull towards the origin. Any distance they are away from origin, they will return to it quickly. The distance decay is exponential. Is that all correct? Is everyone fine with this model answer? Hence, we may interpret origin as the preferred location of the monkey troop. This may correspond to their nesting sleeping site. Let's call it their home. Therefore, the parameter alpha is the return rate to origin or home. I should have written home also.
So this is assuming alpha is positive.
True. You could have, yeah, absolutely true. I did not realize that I thought I had written alpha positive, but I think I did not. That was my mistake. So you were accounting for both alpha positive and negative. I noticed that a lot of you did that, which is very nice. Yeah, but unfortunately, I did not realize that I forgot to write alpha positive and 0. Yeah. So what many of you have done is said that if alpha is positive, x is the equilibrium and stable, and if alpha is negative, it's the opposite. You have written that. But surprisingly, very, very few of you have made this connection to how animals are moving, what it means, what it may mean to animals. I think I would say, when I say very few, of the 23, maybe 3 or 4 of you may have done this. Most of you have just stuck to the mathematical interpretation only. But as long as that's fine, I haven't cut any marks, by the way. I usually haven't cut marks even if you had a mathematical interpretation. For example, I wrote something like, we may consider it as preferred location of monkey, not money true, monkey true. So even if you didn't have this, I haven't cut any marks. No? So is this fine? Okay, now let's look at B. To model the stochastic part, the student assumes that g of x is equal to sigma e power minus mod x. Plot this and interpret the stochastic driver term. So these are some plots for g of x versus x for different sigmas. Okay. I think I forgot to put what the blue, black, and red mean. Blue is the lower sigma, larger sigma. Red must be the small sigma. Okay. Again, a lot of you haven't done this plot, which is very surprising. Okay. That's, but you could have also drawn by hand. Many of you have skipped the question. I guess again, a lot of it has to do with the time. Clearly, the strength of stochasticity in their movement is maximum at home. So Gx basically is sort of stochasticity strength in their movement, right? Maximum near their home, and it decays as they move far away. Origin is their home, as their maximum stochasticity when they are near home, and when they are far away, their stochasticity reduces. This may make sense since animals are most comfortable exploring randomly near their homes than when they are far away. Does this make sense? Do you agree with this interpretation?
Yes, sir.
Yes, sir.
So the maximum answer I think I had got was somewhere here. And I think maybe one student may have written this, something on these lines, but not quite this, but something on these lines. So some of you have written it decays exponentially with distance, which is basically a description of the function itself. Okay, it's fine, but but this is what I was expecting. Okay, but this makes sense, no? Is the interpretation also fine? Okay. Okay, now part C. Okay, so what I thought was that most of you will do part A and B, and you may not be able to C at all. Okay, but it turns out that many of you have done C and have shown lots of results. So now, here's my comments before I show any results at all. Let us think a bit about deterministic and stochastic drivers acting on monkeys. Okay, they're actually acting in opposite directions. Do you agree with this? While the deterministic pull is maximum far from home, right? This pull is towards home, right? The stochastic forces are least there. And now look at what happens near their homes. Near their homes, which is origin, deterministic pull is small because alpha x becomes 0 there, right? Whereas stochastic movement is maximum. Actually, I think there are a couple of you who did write this. They're acting in opposite directions, which was actually very interesting. But you notice this pattern. Okay, is this clear to everyone? Does everyone agree with this?
Yes, sir.
Okay. So now basically how exactly animals will move depends on this relative strengths of deterministic and stochastic forces. Do you agree with that? If there are two opposing forces, their relative values will now tell what will happen, right? So alpha is the return rate to home, sigma is to wander away randomly, right? So the relative values of this will tell you results. And whenever you have, there are two parameter values, right? It's always important to think of three regimes. I have written two here just for as running, I was losing my patience in writing. Okay, since I fixed alpha is equal to 1, right? Just go back to the equation. See, alpha comes in this part, right? And sigma comes in this part, and they both come as a coefficient to these terms, right? Which means that alpha and sigma are sort of comparable numbers. Their effects might be comparable. Is that reasonable to assume? Assuming that g of x and f of x are also of similar order of magnitude, right? Alpha and sigma are can be comparable numbers. Now what that means is that I can now that I have fixed alpha is equal to 1, now you are basically what you need to do is you have to consider different values of sigma. And how do you choose this? And that's always very, very important. Choose different sort of regimes. For example, one regime is sigma much smaller than alpha, and the other would be the exactly opposite, right? And I have now basically shown here results. Okay, the red corresponds to sigma 0.1, which is much less than alpha, right? And sigma 10 is the exact opposite of it. And what many of you have done, which is of course what I was expecting, and I haven't cut marks at alphabet, is that you basically will most of you have considered some values, but they haven't spanned. You haven't spanned the entire range. Some of you have just stayed sigma greater than alpha. Some of you have just stayed sigma less than alpha. But I think very few of you, I think maybe one or two, I think two of you, maybe three of you actually explored the entire range. Okay, which again is given time constraints is totally understandable. Okay, so this is what. So now, do you observe time series? Do you think they are dramatically different? See, there is one obvious difference here between how location is changing over time, which is the red one is very, very close to origin, right? And the blue one is much more random, much more going far away. You may ask, so what's the big deal, right? Obviously, when there is a lot of stochasticity, of course they will wander off, right? Okay, is that the only difference between red and blue curves here? Or is there something more? Which is why I had also asked you to plot the histograms. Okay, histograms show something very, very interesting. So if you look at sigma is equal to Z1.1, small amount of noise, where are animals most likely found? They're all found near 0, right? However, for sigma 10, what happens? Are they found near 0? What is 0, by the way? 0 was the
Origin.
origin, their preferred home, right? Their deterministic home, right? Let's call them deterministic home. They have a preferred home at origin, right? If you consider only deterministic term, right? So that's where small amount of noise will just make them roam around there. But when the noise increases, what happens? They're not spending. The deterministic forces have basically weakened now. Okay, what's now happening is that their most likely locations are somewhere like -2 and +2. They're basically now mostly driven by a lot of stochasticity. Whenever they come near home, they're moving so randomly that they end up far away from home in one direction or the other. But can they keep on moving away? No, because they do have that minus alpha x pull towards home, right? They do want to come back to home, but they're but they also have very lot of randomness. But because of which what they do is they end up spending more time slightly away from home in both the directions. Do you see this point here? So usually whenever we think of noise, what you think is you have, if 0 is a deterministic equilibrium, okay, that's where the system will be, system will stay. Small amount of noise will make them spread around deterministic equilibrium, right? More amount of noise will make them do like this, right? A bigger distribution around deterministic stable equilibrium and so on, right? But what happens here is something very interesting, right? When the noise increases, suddenly what happens? They actually move away from the stable equilibrium. And that's very interesting aspect of this model. Okay, and these type of behavioral changes, when that happens because of stochasticity, they happen only when you have multiplicative noise. So let's go back to this equation. So only if g of x was a constant, you will never see this behavior. You will see this behavior only for multiplicative noise problems. Okay, multiplicative noise means that the strength of noise depends on the state itself. Okay, Okay, and these kind of multiplicative noise usually you don't find in physical systems. In physical systems, you mostly find additive noise where g of x is equal to constant. But in biological systems, you can actually find g of x to be multiplicative, and those can actually cause what these are also called noise-induced states. So the two new states we have found now are on -2 and +2. They're entirely a consequence of stochasticity. Okay, so these are the main findings now for small stochasticity. Histogram peaks at or near origin, hence animals are mostly around origin, their home. For large stochasticity, histogram shows bimodality, away from origin. Hence, animals are most likely found away from home at these 2 points. Is it fine? Okay, and what's the intuition behind it? This is because for small sigma, deterministic pull dominates the system and hence truth is near origin. For large sigma, exactly the opposite happens. Okay, and it's the balance between the two that causes this new preferred locations. Okay.
Yes, it's clear.
Any questions on this? So the difference between this and this is not just quantitative. It is not just it's becoming more and more random. It's actually becoming something fundamentally different as you change noise. Okay. Okay, so let's go to the another question on question 5. So this was a different animal which had a different deterministic. I think I messed up here by the way. Okay, different equation here, and this equation is a bit more complex. Beta x into 1 minus x into 1 plus x. It's a cubic equation now. Okay, so if you plot this equation for beta greater than 0. So I wrote beta greater than 0 here, but I forgot alpha greater than 0 in the previous one. Okay, so what you will find is that 0 is the unstable equilibrium, -1 and +1 are stable equilibrium. Okay, so this is like saying the position of herd has preferred locations of +1 and -1. Maybe they are good foraging grounds for zebra. Okay, let's look at what I have written. Deterministic equilibria are 0, 1 and -1. Since beta is greater than 0, x star is unstable. So basically you could have found this by just plotting that function f of x for positive beta. So you don't have to actually solve f prime of x star and all. Okay, so always use graphical methods. They are very, very powerful. They can help you, and you can use the graphical plotting tools also, right? Okay, so 0 is unstable and minus. This is unlike the previous example I told you, where 0 was the stable, right, for the monkey troop question. So therefore we can interpret my +1 and -1 as preferred locations. Okay, and in contrast, origin is not a preferred location. Is that fine? And the parameter, what is parameter beta? It captures the rate at which herd moves away from the 0 equilibrium. That's the most precise definition. But as long as you got some element of rate of change of movement or something like that, I have given you marks. Is for part A clear now? So part B is plot just a simple quadratic function and interpret it. Okay, so I haven't done the plotting here because I thought it was a simple quadratic function anyway. What this shows is that it has the opposite pattern. It has, if you look at this, the stochasticity is minimum at x equal to 0, and it increases as you move away from 0. Is that right? So even here there is the same element of opposing forces. Okay, they are again acting in the opposite directions. Deterministic. What is the deterministic term doing? It pushes system away from 0. It is it doesn't like 0, but that is also where the stochasticity is minimum. Okay, the stochasticity is much more as you go towards the stable equilibrium points. So there is again this tension between the two. So now if you now do simulations, you find this. Okay. So I'm showing you two results here. The red ones are for small sigma. The blue is for large sigma. Okay. Again, it looks like there is more stochasticity in the blue compared to red, obviously. Of course, but if you actually plot the histograms, you find something very different. Okay. If you take small sigma, you will find a mode either at -1 or +1. Okay, I have plotted only for one trajectory here, so you have only one here. But you could, for large sigma, you can also find, you will actually found a mode at 0. Remember, 0 was the unstable equilibrium, right? So because beta was positive, if I go back to this, because beta was positive, 0 was an unstable equilibrium. However, when the stochasticity is large, the zebra herd is now basically found near origin. Okay. Of course, here the interpretations of why exactly zebra should have this kind of stochasticity is a bit random. There is no, because without knowing why it came from, you can't really say. You can only interpret the given equation. Okay. Is this clear now? It also has exactly sort of similar property like the other, where stochasticity changes the type of observed states. Again, these are called noise-induced states or noise-induced transitions. Is this clear? Any questions? Can I unshare now?
Sir, in the previous version of this question,
yeah,
we used eta of t as exponential minus mod x, right? Like, I mean, why didn't we use the bell curve? Is there any reason?
You could have used. You will, I think, for the same results. Yeah. The location of the modes will change, but I think the results will be the same.
One question.
Yeah.
Is there any way to find where the modes will be in the stochastic system?
There are methods, but they're mathematically a bit heavy. So I usually cover them in my advanced course.
Okay.
Yeah, there is a method called master equation and Fokker-Planck equation in stochastic processes and physics out of literature. So we can use them to analytically get where once you add stochasticity, where the modes will be.
Okay. So it's not trivial, like you cannot look at the graphs and say something.
No, it's quite involved. Yeah, it's possible. One can intuitively argue out. You can see here we could argue, right? So simple enough, but if somebody were just given the equation, I think it would still be very hard to guess that, oh God, they actually become two different modes and they go away from stable equilibrium. Is actually a hard thing to believe. If you think about it deeply, you have such a clear exponential decay towards origin here, right? But the noise actually turns that around is quite a very novel result. It's actually not a non-trivial result.
Right. So I was thinking along the lines of how we interpreted the system with harvesting. So there we looked at the points where the logistic curve and the harvesting function, the functional response curve intersected. And those intersection points corresponded to the equilibria, right?
Yes.
So I was thinking, Alex, whether
is there a method like that? Yeah, there is. Maybe there is an equivalent method. It requires more work, much more mathematical sophistication. Yeah.
Right.
See, because I said, stochasticity is a pretty difficult topic, and I thought it's very useful to introduce it, although it is difficult, because all of the biological world is stochastic. It has strongly influenced by some type of stochasticity or the other, right? So I think knowing some methods to simulate, even if not analytical calculation, even to know, if you know how to simulate this, I think it's a technique that actually is useful in today's research. that very few people actually know, which is why I introduced this, although it's slightly difficult, and I will not be able to obviously cover a lot of other related techniques associated with it. For example, in the last Thursday, just 2-3 days ago on Wednesday, there was a talk from a physicist working on microbial ecosystems. He looks at how microbial populations, how can we explain, population density, or communities of various microbes. It could be in our gut, it could be in soil bacteria communities, and so on and so forth. And the kind of equations they use all have this form, very simple form, where f of x is simple logistic model and g of x is just x. Okay. But at least knowing how to simulate such equations will be sort of already a will make you sort of when you see an equation, you won't feel intimidated if you read a paper of that type. Any other questions?
Is there any way we can know the distribution? You told we couldn't see, but is there a possibility?
Say that again, sorry. What is the question?
Know the distribution of marks somehow? Like which questions is it?
Okay. So distribution, I think you should be able to see, no? You can't see. Did you have 2 attempts, Aprupa? Did you have 2 attempts? If you had 2 attempts, then in one of them, you must be able to find the distribution.
Yeah, if you just go to the quiz and click on the quiz, you can choose either attempt, and I might came in attempt 1, but it can be other one. Yeah.
Okay. Any other more exam related questions about grading or any of these things? So now we can also sort of just, if there are no more questions about the exam, we can discuss sort of slightly broadly, sort of, summarize what we have learned so far, and, sort of make sense of it. Is that fine? Because I want to start a new topic from Wednesday. Yeah, it is. Rashi, you had a question? I don't know. You have a question?
Can you just explain that histogram? And like, how did you get it from the?
Hi, Rashi, I can't hear you at all.
Hello, am I audible?
Yeah. Yes.
Yeah. From the like the noise graph, how did you manage to go to that frequency histogram? Could you just explain that once?
Oh, okay. I can send you the code from here to here.
Yes, sir.
Here to here. So if let's say if you have a variable x where you have stored all the values over time, let's say there is a vector x where you have all the values stored, just write HIST histogram x, HIST of x.
Okay. Yes, sir.
That will give you this. I can maybe send you the code that does this exact thing. Okay.
Yes,
any other
thank
questions? Sure. Yeah. Don't worry about the marks, because this is a course with continuous evaluation. So doing badly in one thing just doesn't hurt much, I think. So I want one more feedback. So I was wondering, so usually in this course, because the number of students are large, it's very hard to do things like presentations. But would you still be interested in, let's say, doing one sort of paper presentation? Let's say that sort of takes, one sort of, extension of whatever we have covered, and then maybe I don't know how to manage presentations of 40 people. It will be huge. But is this something that you would all like, or would only prefer current mode of assignments and lab assignments?
It means that we doing presentations, is it?
Right, yeah.
I thought the paper presentation was something else.
Say that again, sorry.
No, we had the other paper presentation explaining a paper, I thought.
Exactly, that's precisely what I meant. Yeah.
Okay.
Explaining a paper, yeah.
It might be interesting to just discuss a couple of papers together instead of doing paper presentations for the whole class.
Take a few, say that again, Sean.
Like just discussing a couple of papers, like interesting papers that either you suggest or we suggest, and sort of discuss it with the whole class instead of doing individual presentations might be interesting.
Okay. So I just tell, okay, no, but please read these papers and come, and then we'll discuss those. Is that what you meant?
I mean, something like what we do in lab,
yeah,
it will be similar only.
I didn't understand the mode though.
I think like a group presentation of a particular paper.
I can't hear you, Rashi. I couldn't hear
the group presentation of a particular paper, like an entire group presents one paper, so that we can work around.
Something like that is probably manageable with 10 groups. A 15-minute presentation of a paper, we can cover some 6 groups in one day and another 6 groups in another Friday, something like that. Okay. Yeah. Okay, I'll think about it.
I think it would be interesting because, like you said, that you would not explore everything. For example, take stochastic differential equations, right? So if you give us a paper on that, maybe if one group could read up and explain about it very briefly. Yeah, it would be sort of interesting.
Okay, maybe you mean an application of that, not about the SDs themselves. An application in one, let's say one real data context, for example, right? Yeah. Okay. Yeah, true. Okay, I'll think about it. I have to think of papers that are sort of feasible to read and present. Okay, I will think. So, for example, so the thing is, the next set of topics I'm going to cover. So, on those topics, it might be quite difficult to think of papers. So maybe I will think of 2-3 types of topics. One on population dynamics and density dependencies. Okay, how do people make connections between theory and data? Okay, and the second one I could think of maybe again something on this ecosystem dynamics. Okay, using these frameworks. The third one could be something about these kind of stochastic differential equations, how they have been applied in different contexts. I will try to come up with a pool of papers, maybe 10 to 15 papers, and I will try to organize and see if it's feasible. Okay. So let's now quickly think of sort of I just want to sort of give a maybe 10 minutes of overview of what we have learned and where we stand now. Okay. Okay. 1 second. Yeah, you're able to see this new screen. Okay.
Yes.
Okay, fine. So what we have done so far is, we have tried to basically deal with very simple models, right? They are called basically, we have basically been looking at single species population dynamics, right? And then we have basically thought of formulating them either in a discrete generation framework I don't know why it's writing in a very crazy way, or in the form of a continuous time framework. Okay. And then we have studied various implications. What we have done is, hey, look, let's incorporate very basic features. For example, competition, intra-specific competition. Okay. And then we have thought of incorporating things like, harvesting, or sort of, predation, where the dynamics of predators are not very important. And then using these simple processes, what we have done is we have tried to study implications. Okay, what are all possible dynamics that's possible, that are, that can happen in this simple modeling context. So one can also ask a very simple question, a sort of strong criticism of theory-based approaches is that, hey, look, you can write all these models, so what? And that's the sort of, criticism that a lot of empirical sort of, people will argue, and which is why we read in the very beginning, what is the sort of philosophy of modeling? What is the purpose of writing these mathematical models? So there are sort of, I think there are two main purposes of writing sort of, these kind of mathematical models. One is, but by writing mathematical models, we make our arguments a lot more precise, and we sort of exactly know what are the assumptions we are making and what are the assumptions that we are sort of, important, what are not so important. So I think that actually lays out very clearly, and it also sort of provides a mathematical foundation or formulation of those assumptions. For example, even when somebody does experimental work, empirical work in the field, they have a model in their mind. It is just that it may not be expressed mathematically. Okay, it is expressed verbally. So what we have done here is we have shown that even in the context of single species models, by explicitly writing down these assumptions in a mathematical form, we can obtain really rich dynamics, and therefore one must be cautious in understanding how populations and ecosystem behave. And if you were to say what are, and what is interesting is that these implications would be very difficult to sort of arrive at in the absence of such a mathematical formulation. And in some sense, that's one important justification of why one must be doing mathematical models, because they will help you abstract the problem of biology, which is very, very complex, and it will help you quantify things. It will help you think of what are we measuring. Can we do some measurements which are not obvious? Can we do some measurements which are non-trivial? And are there some dynamics that are something we are overlooking? For example, think of the idea of periodic cycles, right? Periodic cycles that are entirely intrinsic. Okay, chaotic behavior that's entirely intrinsically driven in deterministic systems, or the idea that there are multiple stable states. And these sort of implications are difficult to arrive at in the absence of mathematical models. And the consequence of multiple stable states, if you have read Sheffer, is that of catastrophic shifts in ecosystem, right? So these kind of implications and these kind of possibilities are possible to think of only with the aid of mathematical models. So once we study implications, that is, that was sort of bread and butter of theoretical ecology for a very long time. But now people demand more. Okay, make better, connections with data. Okay, you can't just keep on running, these, elegant mathematical models that are sort of, have very simplistic assumptions, and therefore, even though they may show all these interesting features, they may not be really useful. So there has been a lot of effort in also doing this, and in that direction, the framework of stochastic differential equation is really helpful. Okay, because it helps you simulate stochasticity and sort of discover dynamics which are actually not possible otherwise. Okay, and maybe what I can do is go in the context of, you know, multiple stable states. I can sort of suggest 2 or 3 papers where people have used and tried to make some very interesting, you know, experiments and you know, and also being able, you know, and test those theories. And another thing ecologists will be often interested in is, okay, you have all these models that talk about implications, and then of course there are models that try to explain observed patterns. Okay, that's another type of modeling. You have observed some patterns, and therefore you now use the aid of all these mathematical models, sort of you explain them. For example, you know, the paper by Sheffer is a very good example of that. You know, it documents, you know, some various types of this ecosystem regime shifts, right? Okay, now that you know, there are these simple mathematical models that explains the existence of multiple stable states and switches between them. And there is this concept of hysteresis. Was it also covered there? The concept of hysteresis?
Yes,
I think I
yes,
also briefly explained.
yes.
Okay, so that, you know, you can explain hysteresis using very simple mathematical models. Okay, that's another, you know, usefulness of these, you know, these approaches. You explain the observed patterns. Again, you know, we need to think better. You know, is it one is implications, broad implications. Second one is what are the explain the observed patterns, and being more ambitious, can you actually make predictions, right? For example, can you say that, you know, this forest will die off? I mean, you know, of course, what is die is a subjective question. You know, this forest will undergo this kind of you know, behavior. Can you, you know, kind of, you know, can you use mathematical models now? Can you develop this further to make predictions? Okay. For example, let's take this simple example of this catastrophic shifts. Let's say we have this time. Somebody is collecting lots of data about. I think the paper talks about lakes, right? So let's say P is the phosphorus concentration in lakes. Okay. In lake water. Let's say it's showing this kind of patterns. Now, how do you know that this phosphorus will suddenly increase and become very large? Because we know that lakes have this tendency to have multiple stable states. They can have what are called these, you know, eutrophic states, which are full of algal blooms, right? Whereas this could be a what is called an oligotrophic state. So let's say if I'm in this oligotrophic state, is there some way that we can say that, you know, I'm entering a danger zone here, and therefore I'm switching to a eutrophic state? Can your mathematical models be used for such predictions? So those are the challenges, you know, those are challenges that researchers are still figuring out. How do we address these kind of questions? Okay, so and what is very interesting is that the current level of mathematics that we have learned is just good enough to actually start reading papers that tries to address these kind of problems. Okay, so which is why I think, you know, some of these techniques are actually really powerful, although they are very, very simplistic. Okay, so this was a short summary I wanted to sort of discuss in the context of what we have done and how do we sort of make sense of these models. So I will stop here. So let me know if you have any more questions, and we can discuss them, or we can then begin on Wednesday on a new topic.
technically, there should be models even in the biological systems, right? I mean, we may not be able to what is mathematically tell you all those things, but there should be, I mean, some order or model which they are following. I'm just asking.
So you're saying that I don't understand. I don't think I understood your question clearly. So of course there are mathematical models in biological systems, and we are studying them. So what was your question?
No, I meant so. How do I put it? Just a minute. Give me a minute.
Any other
I'll
questions
think
in the
over
meantime?
it.
Sure. Yeah. Any other questions in the meantime? It's also important, as I say, one of the goals of this course is not just to learn 25 different models. I think the purpose, in my opinion, of this course is also to learn mathematical modeling. Okay, for example, instead of the way I have tried is, I have tried to go in depth just about single species dynamics. I could have also chosen an alternative approach where by 6th week now, right, I could have covered 2 species models, 4 species models, trophic web models, and so on and so forth. The reason I haven't done is that we want to understand one topic in depth. Therefore, if you can actually, I would like to enable you to learn on your own more topics. If you take a classic books on ecological theory, theoretical ecology, they have lots of varieties of models. What I'm hoping is that by learning one topic in depth, you can actually go and read a lot of things on your own. Okay. So I would like you to think, critically, how do we build models? How can, and also given a context, how can I construct a model? And how do I analyze the model? That's also very important, tool to learn. And then, but also think beyond models. How can I make it actually more useful to understanding observed phenomena? How can we make it useful in terms of predictions? How can we make more interesting in terms of providing new insights? Okay. So if there are no questions, we can stop here. Okay.
So I don't have a question about this, but if no one else has a question, I have another issue that I would like to raise.
Sure.
Yeah, so the bio majors from my batch, that is UG second years, we have our UG biochemistry exam scheduled on next Friday afternoon.
Okay.
So if you conduct a lab, we will not be able to attend it live.
Okay. So what do we do? So how about for you all Friday and Saturday afternoon? We can just do that. Is that fine? So maybe I can do one thing. Would you be willing to? So anyway, next Saturday was planned as a backup, or a makeup class, right? To cover up the missing classes. So what we can do is, I will need anyway. In fact, Wednesday 1 hour will be very short for me to cover the background I need to cover to give you a lab assignment. Okay. So what I can do is I can do 1 hour on Wednesday, maybe 1 hour on Friday, and then maybe on Saturday we can have the lab. Is that fine?
Yeah, sir. That
actually works better for me also in some ways, because Saturday long classes are also hard for me. Okay, so if everybody is fine, we will just do that. Okay, but not everybody is present today, so there'll always be somebody who has a problem. So I don't know what to. Do you have a representative class here? Do you have people from all the UG batches, the 3rd year? I think 4th year, 5th year shouldn't have a problem usually. 3rd years will be the one that may have a conflict. But anyway, I had announced about the makeup classes long back, so hopefully it's okay. So we can do the lab on Saturday. That works better for me.
Thank you, sir.
Thank you. So I will stop recording now.